So now we're back to Kaggle's Intermediate Machine Learning cross-validation. So this is a better way to test our models. All right. So remember, it says a better way to test the models. We're not actually going to be making the models more efficient here. It's just a better way to test them. So let's go. In this tutorial, we're going to learn how to use cross-validation for better measures of model performance, okay? So here's the introduction. Machine learning is an iterative process, true. We will face choices about what predictive variables to use, what types of models to use, what arguments to supply to those models, true, etc. So far, we've made these choices in a data-driven way by measuring model quality with a validation or holdout set, okay? But there are some drawbacks to this approach. To see this in our minds, we're going to imagine that we have a data set with 5,000 rows. Okay. We will typically keep about 20% of the data as a validation data set, as we've seen before, or 1,000 rows, obviously. But this leaves some random chance in determining model scores. That is, a model might do well on one set of 1,000 rows, even if it would be inaccurate on a different 1,000 rows. Turns out. All right. So, at an extreme, we could imagine having only one row of data in the validation set. That is too extreme for me to imagine. Why would that ever happen? If we compare alternative models, which one makes the best prediction on a single data point will be mostly a matter of luck. Absolutely. I mean, but that would be crazy. Anyway, whatever. I mean, just one row, whatever. Okay. So in general, the larger the validation set, the less randomness, also known as noise, there is in our measure of model quality, and the more reliable it'll be. Unfortunately, we can only get a large validation set by removing rows from the training data, which is even worse. And smaller training data sets mean worse models. True. So what are we going to do? So what is cross-validation? The name of the lesson anyway. So in cross-validation, we run our modeling process on different subsets of the data to get multiple measures of model quality. Okay. For example, we could begin by dividing the data into 5 pieces, each 20% of the full data set. True. In this case, we say that we have broken the data into 5 folds. All right. So we can see here we've got the training data, the training set, or the full data set. We got 20% of it as the validation in the first one, and then the rest is going to be training data. And then we have a second experiment, and we just say the next 20% is going to be the validation, and then the rest of it's training, and then so on and so forth. All right. Then we run one experiment for each fold. So in experiment 1, we use the first fold as a validation or holdout set, and everything else is training data. This gives us a measure of model quality based on a 20% holdout set, believe it or not. In experiment 2, we hold out data from the second fold and use everything except the second fold for training the model, just like we just went over, all right? The holdout set is then used to get a second estimate of model quality, okay? And then we're going to repeat this process using every fold once as the holdout set, Putting this together, 100% of the data is used as holdout at some point. Sounds good. And we end up with a measure of model quality that is based on all of the rows in the data set, even if we don't use all rows simultaneously. True. Interestingly true. I just wonder what would happen if we shuffled it up and did it again with different rows in the 20%, but who knows? Let's just keep going. So when should we use cross-validation? Cross-validation gives a more accurate measure of model quality, which is especially important if we're making a lot of modeling decisions. Yes. What? Hold on. Cross-validation gives a more accurate measure of model quality, which is especially important if we are making a lot of modeling decisions. More accurate. Of course that's better. Anyway, let's go. However, it can take longer to run because it estimates multiple models, one for each fold. It takes if we're using 20%, it's going to take 5 times as long. Trust me, I've already done the exercise on it, and it takes a long time. All right, so let's go. So given these trade-offs, when should we use each approach, okay? So for small data sets where extra computational burden isn't that big of a deal, we should run cross-validation. Okay, so for small data sets, small data sets basically. For larger data sets, a single validation set is sufficient. Our code will run faster, and we may have enough data that there's little need to reuse some of it for holdout. I mean, that makes sense. Like if we have a lot of training data and a lot of validation, it just makes sense that we're not going to need to go too crazy with this stuff. Anyway, whatever. So there's no simple threshold for what constitutes a large versus a small data set. But if our model takes a couple minutes or less to run, oh man, it's probably worth switching to cross-validation. Oh yeah, man. A couple minutes to run, just staring at the screen, right? Better have some solitaire, some Minesweeper queued up, right? Anyway, alternatively, we can run cross-validation and see if the scores for each experiment seem close. If each experiment yields the same results, a single validation set is probably sufficient, but we still got to run cross-validation on it anyway. So who knows? Honestly, I don't know. Let's go to the example. So we're going to work with the same data as in the previous tutorial. We're going to load the input data into big X and the output data into big Y. It's not the same. It's not the same. It's not the same because we're going to be using a 5-feature list on this one, which is going to make it completely different than the last few and whatever. So we're reading the data. We're making a subset of the predictors. We got a big X that's going to be data of the columns to use, which is just these 5 features right here. And then we're also going to do a data.price for Y, right? We don't even have to drop it. We don't have to drop price or anything because we're just using the features. Anyway. So then we're going to define a pipeline that uses an imputer to fill in missing values and a random forest model to make predictions, okay? While it's possible to do cross-validation without pipelines, it's quite difficult. I believe it. It was difficult when we weren't using cross-validation. So using a pipeline will make the code remarkably straightforward. True. All right, so let's check it out. We're importing random forest. We're importing the pipeline and the simple imputer. We got my pipeline now equals pipeline. We got the steps. We've got the list full of tuples. List full of tuples. What is this? The list full of tuples. There we go. And then we got the tuples. The first one's preprocessor with the simple imputer. Then we got the model with the random forest in there. Estimator's 50. Random state equals 0. Pretty standard stuff. All right. So we obtain the cross-validation scores with the cross-val score function from scikit-learn. And we set the number of folds with the CV parameter. All right, let's go over here. And then let's come back. All right, so we're bringing in cross-val score. And then we're going to multiply by -1 since scikit-learn calculates negative may. Turns out. I mean, I didn't know that. Anyway, so scores equals -1 times cross-val score, that thing we made up here. Yeah. And we're going to do my pipeline is going to be the, what is it? Is going to be the estimator. Then we're going to have the X and the Y. So we got the X and the Y here. Y could equal none, but this time it equals Y. And then we got this. I don't know what that is, honestly, and it doesn't tell us what it is. I don't know. Anyway, and then what else do we got? And then we also got a CV equals 5. So let's go down and check out what CV is. So CV, int cross-validation generator or an iterable. The default's none, but we're making it 5 to use a what? None to use the default 5-fold. So if we would have put none, it would have done this. It would have done the default. It would have done 5 as a default, but I guess whatever. And then we could have put an int to make it 6 or 4 or whatever. And then we've also got this scoring neg mean absolute error. Let's go down to score. Come on, where's score at? Oh, here, scoring. Hold on. Scoring, okay. So scoring, and it's going to be a string. We're going to see this in just a second. We'll just open this now. We got scoring right here, and it's going to be a string or a scorer callable object, which I don't know what that is, but if we go way down here, we can see we've got neg mean absolute error right here. And we've got so many more we got to figure out and learn about, but whatever. Anyway, and that's that. And then we are going to print out the May with the scores. And we can see we get a list of 5 different scores right here because it's broken up into 5 and did it 5 times, right? And we can see also, remember we only have 5 things in our features list. So these numbers are way higher than usual, right? But I'm pretty sure also that's because it takes forever to do this. All right, so let's keep going. So the scoring parameter chooses a measure of model quality to report. In this case, we chose negative mean absolute error, okay? The docs for scikit-learn show the list of the options. We just saw it. And it's a little surprising that we specify negative May. Scikit-learn has a convention where all metrics are defined, so a high number is better. What were we using if we weren't using this? I don't know. Anyway, I mean, because that's why we've got this negative numbers, because we got this -1 here, is because this makes it come out negative? I don't know, man. I don't know. This is so opaque. Whatever. So using negatives here allows them to be consistent with that convention. The high number better, whatever. Though negative May is almost unheard of elsewhere. And honestly, I don't even know, by this little thing alone, I don't even know. Maybe I should have went and Gemini'd it, but I didn't. We typically want a single measure of model quality to compare alternative models. So we take the average across experiments, all right? So we're going to do this. We're going to do scores.mean, and we're going to take all 5 of these, add them up, divide it by 5, and this is the number we get right here. Okay. It's still way higher than usual, but we used way fewer features than usual as well. Not even any, anyway, we know what's up. So in conclusion, using cross-validation yields a much better measure of model quality, okay, with the added benefit of cleaning up our code. We're going to note that we no longer need to keep track of separate training and validation sets. Yeah. Separate training. Yeah. Look, we didn't. We just needed to do X's data, huh? True. Okay, that's cool, isn't it? All right, let's get rid of that. So especially for small data sets, it's a good improvement. Excellent. So we're going to put our new skills to work in the next exercise. Give it a few seconds. You know how long this takes. All right. All right. So now we're on to exercise, cross-validation, and we'll see you next time.